好的。Good evening. My name is Zhou Qing from Tsinghua University. I'm very glad to have this chance to share my perspective about the safety and protection of autonomous driving vehicle. To those who are in Europe and maybe in United States, good afternoon and good morning. This is a very hot subject, autonomous driving vehicle. You probably see many researchers, many developers, many companies are developing autonomous driving vehicles, and they all care about the safety. But that's probably not the safety what I defined. And if you are driving or you are developing autonomous driving vehicle, and your main objective is to make the car driving smoothly, and instead of when you go out of the door, you hit the tree right away, or you cannot identify a parked car on the shoulder. Of course, that is vehicle safety. But I think that's also the reliability, also the design, right? So the vehicle safety I define is about addressing collision risk. When you have imminent risk, how you handle that. So this is vehicle safety I defined. And we have about 1 hour and mainly cover 3 questions. I hope at the end of today's class and you will agree with me about the 3 questions. And the first one is why future car or future autonomous vehicles will still have accident that cannot be avoided. And the second question is, if we agree that, then how we handle that and how we protect that. Can we do better than today's car? What I call that the smart crash protection, and using autonomous driving vehicle technologies, we can enhance the vehicle safety at least better than today's cars. And the third question is simple. And if we want to develop vehicle safety for autonomous driving vehicle, what approaches, what tools, what methods we should develop today? And also I want to share those research results we have obtained during the past 5 years, which is a government-sponsored project. Okay, first question. Do we expect a collision accident in the future car, or are there any accident that unavoidable to autonomous driving vehicles? To discuss this question, I want to assume the best scenario is we assume the car or the autonomous vehicle has the best capability for sensing and for intervening vehicles. I call that near perfect capabilities. By assuming near perfect, of course we haven't reached that near perfect capability, but by assuming near perfect capability, I mean we can sense everything we want to see. So no default about the sensing, and we can make right judgment and the right decision to intervene vehicle, to make the vehicle respond at the best situation or the best operation to handle the current traffic or risk, and the car can be driven well. So this is what I assume the best capability or the near perfect capability. Now how we address the risk, or how we argue the car will still have collision in the future by assuming this near perfect scenario. Let's analyze the problem from the perspective of vehicle intervention or vehicle response. and constraints of traffic environments. Basically, that's vehicle dynamics and geometry, because the car has to move, right? In a certain environment, there must be some geometrical environment, right? You cannot hit the guardrail, right? And vehicle dynamics means and to intervene or to respond to the environment. And the car need some operation or need a time to respond. I forgot the, I forgot to run the slides. So this is the content or the 3 questions we would like to do today. And I forgot the slides. The near perfect capability, and we would like to analyze the problem from the perspective of vehicle intervention and the constraints of traffic environment. Okay, so that's the 2 slides I missed. Okay, I only turn on the slides on my computer. We have 2 computers and 2 cameras, and much complicated equipment. But the good part is we can broadcasting to the whole world. All right, so let's first see 2 cases. Of course, they are not accidents of autonomous driving vehicles. We haven't got automated car on road yet. So I selected the 2 accidents of traditional cars. Let's see this accident. If we assume the black SUV, we'll see the video several times. You see the black SUV turning over, right? We assume the black SUV is automated car. And in this environment, the traffic velocity roughly is 100 kilometers per hour. And see the white truck, the white truck. The white truck, for some reason, all of a sudden lost control. We don't care about that. That's just hazard. So the truck all of a sudden lost control and collided with the black SUV. Let's analyze this accident. So you see, we'll see this video several times, and see the white truck coming, and for some reason it lost control and it hit the black SUV to the side. Then we analyzed the video and we found out the time from the observable kinematics change of the truck or of the hazard to the collision was only 0.6 seconds. So let's say the SUV, the black one, is an automated car. You must have some information to sense, okay, there's a hazard coming, right? So here is the emergency of hazard is the white truck losing control or has kinematic change, has sudden kinematic change. From that time to collision, only 0.6 seconds. Then let's see the traffic environment. Considering this black SUV sense the hazard coming, what can the car to do to avoid the collision, right? Then we assume it has a BAS capability. It can either accelerate or decelerate. With a BAS capability, 0.8 g acceleration or deceleration. And at most, it can move about 1.4 meter from the collision point. So it's either accelerate to drive 1.4 meter farther than the collision point, or hard braking 1.4 meter away from the collision point. So that 1.4 meter is still within the collision point. The truck is, right? So the accident cannot be avoided. This is already situation we cannot achieve. Then we should also assume there must be some delay, right? The car, the SUV should see or should take some time to see the hazard and take some time to respond. then we assume it will take a 0.3 seconds, 0.3 second to make the judgment and to make the mechanical delay. So there's only 0.3 second left. So if we recalculate within 0.3 seconds, it's only 0.35 meter. So it's still around the collision point. So the conclusion is clear. The accident in this situation, no matter how perfect of the technology, the accident cannot be avoided. Because the hazard is all of a sudden is emerged from nowhere, from somewhere. And the black SUV has insufficient time to respond. So I think that you will agree. And we'll see this kind of accident all the cases. Let's see the second case. Okay, the second case is 3 cars. There's a car who was taking video. Let's assume in this car, we cannot see the car from the video. Let's assume this car who was taking video was a highly automated car with perfect capabilities. Okay, from the car changing lane from fast lane to the slow lane, so it changed lane, and its velocity was about 70 kilometers per hour. Then all of a sudden, it says, okay, there's a red color car 20 meters ahead of it. At that time, the velocity was 70 kilometers per hour. And the obstacle was 29 meters ahead of it. And we assume it sees that. It has a 0.3 second delay and perform a hard braking right away, and still it will collide with the obstacle or the red color car at 14 kilometers per hour. So the collision cannot be avoided. The reason is the same, the cause is the same. The hazard all of a sudden appear, fly like the hazard from the sky, right? And the car has no time, doesn't have enough time to respond. And we analyze quite a number of these kind of accidents. We have 100 about that. Then but we only identify about 15 that has video, that we can clearly see the time frame. And the conclusion is, for this kind of accident, usually the time from hazard emergency to collision is shorter than 2 seconds, shorter than 1.8 seconds, around 1.5 seconds. So that's our conclusion. Let's further analyze the problem from the perspective of time in traffic. I made several examples on highway, on normal road in city, or on campus road, and the speed, let's say, is from 120 kilometers per hour all the way to 20 kilometers per hour. So on different road situation, different speed. Then let's assume, okay, you can easily calculate within 1 second, if the car was traveling at 80 kilometers per hour, it will go 22 meters within 1 second. That's not fast, right? And if the car was traveling at slow on campus, 20 kilometers per hour, within 1 second, it can go 5.6 meters. Okay, we assume the car have the best braking capability when the car senses the hazard. So this is the best braking time, or the shortest braking time. And for the 80 kilometers per hour traveling car, when the car want to perform a hard braking, it takes about 2.8 seconds to get a fully stop, and 31 meters. In other words, if there's any hazard within 31 meters, if you cannot see the hazard within 2 seconds, you cannot make a right judgment, right decision within 2 seconds, the accident will be difficult to avoid. And plus, it's even worse is we assume it's perfect, right? it takes a 0.2 second to make a decision. And there's a mechanical delay point, so altogether it's 0.3 second. Let's make the things worse. And this is 80 kilometer per hour to get a fully stopped, and subtracting the 0.3 second delay, and it can stop within 38 meters. And for 25 kilometer per hour traveling speed on campus, 5 meter. 5 meter means you drive slowly within speed limit on Tsinghua campus. Then all of a sudden there's a pedestrian crossing. So the speed, you did not overspeed, right? All of a sudden there's a pedestrian crossing. If the pedestrian is beyond 5 meter or 6 meter, then the car has the best capability to sense it and stop it. You can avoid collision with the pedestrian. If there's a boy running out from like a 3 meter, 4 meter ahead of car, by no ways you can stop your car. Even you see the boy, you still probably hit the boy with like 1 kilometer per hour. So that's we calculate the accident or the accident scenario from the time perspective, and by our calculation or an analysis, for those we call that the near accident time window, usually shorter than 2 seconds. So remember that the 2 seconds. 2 seconds, the only thing you can do is hard braking. Or if you see the other lane has no car, you can change the lane, right? You can do that. That's the only thing you can do that. But it will be difficult to avoid many accidents. Plus, there are many other challenges. So the challenge I analyze is only from the perspective of vehicle dynamics and the constraint of traffic environment. We did not, that's not my major, we did not analyze there are many other problems, right? Sensor errors, network problems, communication delay, and software bugs, hackers, and mechanical failure, possible some defect on road, some design flaws. So all those kind of problems we cannot solve on. So in my analysis, we assume we don't have those problems. We leave those problems to the expert of people who are developing autonomous driving vehicle. So for me, I will handle when you have imminent collision risk, how we do that. So it's difficult to handle 2 computers. All right, so my next question is, can we ignore those corner cases? So the corner cases is an English term. Corner cases means extreme cases. Okay, you can see, yeah, my technology can handle 95% of scenario. Then the question is, do we allow your car to be driven on road if your technology has reached 95% perfection or satisfaction? Can we allow that? Let me analyze for you, okay. Let's see today's accident. Each year, worldwide, we have about 1.3 million fatalities. 1.3 million people die of traffic accident whole world each year. That's by the report of WHO, World Health Organization. So we feel, okay, this is not safe, right? It's not safe because we have 1.3 million people die of traffic accident each year, plus maybe 20 million people injured. Then if I give you another evidence, see the second line, we can also feel it's pretty safe. Let's see the data from United States. Every 100 miles traveled in US each year, there was about 1 person dying. So 100 million miles traveled. That's a huge mileage. 1 person died. So with that probability, we can feel it's pretty safe, right? When you want to take a car to go vacation, you don't expect I will encounter an accident, right? So it's pretty safe, both data point to. And we also know most accidents most collision accidents were caused by human errors. 95%, more than 95% of the accidents were caused by human errors. Then that's the reason we want to do autonomous driving vehicle. We say, okay, let's get the human drivers out of the system. The human driver make mistake. Then would that resolve the problem? The answer, or at least my answer, is no. We can try our best because yes, human drivers, human errors make 95% of accidents for the past 100 years. Then let's see, when we have fully automated cars on the road, whole cars are autonomous driving vehicles, then we do not allow human to drive vehicle. We simply replace error source to computer, right? Get rid of human, then we use computer to drive car. We see computer making mistakes all the time, right? Software bug, hardware problem. So we have to, in the future, we rely on computer sensor to drive the car. We cannot fully trust them. And if I can summarize the characteristics of traffic accidents, today's and futures, is these three statements. For every single trip, there's extremely low risk because the car and the driver and the future computers will make the technology acceptable. So for any single trip, the risk, the collision risk or the accident risk is extremely low. So that's the first statement. And the second statement is we have an extremely high mileage in China, in US, in Japan, in Europe, right? Because we are mobile world, the mobile mileage is a huge number. Then even we have very low accident rate in this extremely high mileage, now and the future, we can accumulate very large number of accidents each year, which will incur very high cost in human life, injuries and fatalities. So very safe for a single trip, huge number of accidents, a huge number of mileage, then large number of accidents and injuries. So that's the basic characteristics of traffic accidents. When we develop an autonomous driving vehicle, we have to remember that to address those so-called corner cases or extreme cases, we must address safety. Otherwise, we will see maybe 5 million people die of each year. Right now, today's number is 1.3 million people die of traffic accident each year worldwide. Okay, what would be our strategy to address those corner issues or corner cases? Again, we assume in the future, we will have satisfactory technologies for autonomous driving vehicles. Let's assume, I'm not developing autonomous driving technologies. Let's assume today we have reached 60% to our satisfaction. Probably not. If you ask those people developing autonomous driving cars, they say, oh, no, it's not 60%, it's far from 60%. Let's assume it's 60%. Then the question is, when can they eventually reach 99%? If they cannot reach 99% safety satisfaction, then we can expect 5 million people will die each year, right? It will be better, it will be worse than today's situation because we don't know so-called those unknown unknowns. If we know, okay, there's a risk on the road, or there's a young driver, they are very reckless, or an elderly driver, they have a slow response. If we know those, we have method, we have approach to handle them. But the most difficult is we don't know what will be happen, right? For human drivers, they keep repeating the mistake. While for computer errors, every time they make different mistakes. You fix one bug, then you cause another bug. And so my suggestion is we cannot and should not fully rely on autonomous vehicles, autonomous technologies alone. We should also rely on something else. If we fully rely on autonomous vehicle technologies, then we probably will never see it can reach 99%, or it will take very long time. We like autonomous driving vehicle. It can provide a lot of convenience, efficiency, and even safety, right? So we should not, okay, you are still 90%, then I do not allow you to be driven on the car. Then if we do that policy, we sacrifice other convenience, other efficiency that the autonomous driving vehicle can bring us. So the answer is, I put that in, sorry, I forgot again. Sorry, I forgot again. And so the answer is smart, I call that a smart crash protection. Smart crash protection. And the so-called smart crash protection, we consider it's a last line of safety defense for autonomous driving vehicles to cover those corner cases. Here's my argument. Let's say we have this autonomous driving vehicle technology under development, and right now it's 60%. Then let's say 10 years from today, it reach 95%. I don't know yet, but let's assume it can reach 95% 10 years from now. But it's still far from the safety goal we require. Then you say, okay, I give you another 20 years, another tons of money. It's very difficult to reach 99%. But if we ask help from crash protection, the crash protection today only cover 1% responsibility. So 99% of accident or the risk are avoided by human drivers. Of course, a lot of mistakes are caused by human drivers, but we have to trust human drivers also avoid a lot of accidents, that they cover probably 99%. Then we, crash protection, only cover 1%. Then we say, okay, in the future, the computer, let's say they cannot do as better than human drivers. And 10 years from now, they reach 95%. Then I will ask a crash protection to shoulder more responsibility. Instead of 1%, let's do 5%. So all things together, we can reach safety goal with 99% satisfaction. So the question is, can we do that? Can we do that? Let's come to my second subject, is I call that the smart and the individualized crash protection. And I'll show you how we can do that. You say, I don't trust you, right? Okay. And here's my argument. I have more resources than today. First, I have much more information. So if I look at today's technology, for crash protection, everything I know is, okay, I have a standard size dummy, crash dummy, sitting in a standard posture. We have standard velocity, everything in laboratory environment. So I cover that laboratory cases. I reach 5-star safety rating. And I don't have other informations, right? Well, in the future, the autonomous driving vehicle keep monitoring the traffic environment. And as soon as you get onto the car, I can detect your body stature, your rough mass, okay, your 70 kilogram, and or 90 kilogram. I roughly know your mass, right? I roughly know your height, your sitting height, and I roughly know your sitting posture. So that's not difficult. As soon as you get onto the car, probably take me 1 minute, I can know everything. Then I also keep monitoring the traffic environment. I know my car speed, I know the other car speed surrounding me, right? I know, okay, this is pedestrian. So I can keep those information I don't have today. In the future, I have those, so I have much more information. So I can pretty much predict the upcoming crash, even so may not be 100% accuracy. So I can send so-called pre-crash warning to the system. Okay, I have a 10% possibility will collect the car ahead of me within 1 second, within 1.5 seconds. Then I also have much longer time as a crash safety, as a crash protection safety. I have a much longer time to charge and to activate safety devices compared to the countermeasure I have today. So let me explain, what do I have today? Today we use a seatbelt, airbag, seat, windshield to protect people. We call that passive, right? So this is an airbag working principle. Today, I don't care anything before the accident. I don't know those information. So the collision point is my time zero. From time zero, I sense, okay, the acceleration or deceleration is all of a sudden increase. Then 100 milliseconds later, the event is over. So the typical crash lasts only 100 milliseconds. That means by halfway, by 50 milliseconds, the airbag must be in place. Otherwise, the people will be killed, right? So within 50 milliseconds, the airbag will be in place. Then the airbag will take maybe 20 to 30 milliseconds to deploy. So that means give me only 20 milliseconds left to make a decision. So today, with 20 milliseconds information, 20 milliseconds time, I can make a pretty good judgment to deploy airbag. That's 20 milliseconds. Then in the future, remember I said I'll have a 1 second pre-crash warning, or no, usually shorter than 1.5 seconds, whatever is 1 to 2 seconds. That's 1,000 milliseconds. 1,000 milliseconds is 50 times longer than 20 milliseconds. So I can use that 1 minute. Even so that 1 millisecond, 1 second, the vehicle cannot stop in time to avoid accident. But I can use that 1 second or 2 seconds to activate the protection devices on the car. So that's my confidence, why we can do better in the future. Okay, then let's continue how we do better. And because if we rely on today's airbag and the seatbelt, we probably cannot do much better. So before I go further, let me analyze if there's a possibility we can protect people better. Let's compare the racing car driver protection and the child passenger using car seat. What do you see in common? What do you see in common? So both are very safe, right? Racing car, they drive car at 200 kilometers per hour and make a collision and walk out of car without injury. Then for kids, the injury and fatality rate is very low in today's environment. What do they have in common? They all use double shoulder belts and many other devices. So making them uncomfortable. So they don't feel comfortable. So if you tie them up, then it will be safe. It will reduce injury and fatality chance when you incur the collision. So that's what we learned. But it's okay, I don't feel that good because it's not comfortable. Well, let's continue. I always reference this test as a cadaver test. Cadaver test conducted at the University of Virginia by Dr. Foreman. So they put a cadaver in a sandbox, then perform a high acceleration crash test. Then they found, okay, this is a very severe test, it's a 60 kilometer per hour crash, more than our safety regulation today, and it's generated 200 G deceleration on spine. Then they found the chest compression smaller than 11%. For those people who did not learn my crash safety course, you probably don't know what 11% means. 11% of chest compression means you only have very minor injury. Acceptable mid-level injury is about 30–40% of compression, or at least 30%. And we see no injury to aorta. Aorta is a major vessel of aorta. So basically, it's a very severe accident, a very severe crash, high loading, then it's minor injury. The reason is they put the cadaver in sandbox. What do we have in sandbox? Sandboxes can provide a uniform, well-distributed loading to the body, just like a racing car driver or passenger, kids using car seat. So if we could provide a uniform loading, well-distributed loading to the passenger, it's pretty safe. They can probably sustain 200 km/h crash. And let's further compare, assess the seatbelt and airbag. The seatbelt and airbag, by all means, we must say they are very effective crash protection means. They have saved many, many lives in the past. But what do we see their problems? The so-called drawbacks. And if you are not the safety expert, you probably don't know that. Here's my summary. So if we analyze the loading pattern of airbag and seatbelt and compare them, we see the airbag load is largely uniform over the space. It can provide loading to your head, neck, two shoulders, chest, right? So it's pretty much largely well distributed in space. However, it is very aggressive in time domain. As I said, the whole crash duration is only 100 km/h. An airbag uses an explosion to deploy. So within that 100 milliseconds, there's probably only 20 milliseconds you want to engage with airbag. You want to engage with. If you engage airbag too early, airbag is too powerful. It's explosion. If you engage airbag too late, the airbag already deflated. So airbag is not uniform in the time domain. And let's see the seatbelt. Seatbelt is always in place to protect you, right? You buckle up. So before accident, after accident, even after you died, seatbelt is still there, right? So seatbelt is always in place in time domain. But it only loads your body in a very narrow band. I put the picture there. So the seatbelt load, so it's not uniform in space. It's uniform in time, but it's not uniform in space. So after we analyze all those knowledge, all those points, then we come to the my proposal. We learned from racing car or from child car seat. We call that the adaptive and the uniform occupant restraint. We want to resolve the defect, or not defect, we want to resolve the drawbacks of airbag and seatbelt. Okay, let me explain that later. First, let's explain what I define the uniform load. Uniform load is we apply restraint load well distributed on human body on those strong parts, two shoulders, head is pretty strong, and the pelvis and the leg. So we only apply load. We only apply load by pink color. We only, don't ask me, later I'll show you how I apply load. So I only apply load to those strong parts, knees, shoulders, head. I don't want to apply load to abdomen, right? And to those strong parts, it's well distributed part of human body. And we also apply load, different load level to different scenario. For example, if you are big guy, very heavy, I apply larger load. If the crash severity is severe, it's 100 km/h crash, then I make my load higher. If that's only 30 kilometer per hour crash, I lower the restraint load. So the load is adjustable according to crash severity. And the load is adjustable according to your body size. That's called adaptive. Adaptive to crash situation. How I can do that? Because remember I said we have much more information. We have much more information than before, right? As soon as you see there, I know your body size. And this way we can provide, I call it a protection to a wide range of crash severity and a very diverse body stature. And but you would say, okay, it's not comfortable, right? Like a kids or like racing car. Here's the use scenario I define. Okay, no restraint in low risk situation. Okay, you sit onto your car. It's autonomous driving car. You don't drive car, right? You don't have driver license. As soon as you get onto a car, you go sleep, you go internet, and you take a break, you drink coffee. So if I see probably 90% of situation, we don't have any risk or very low risk scenario, then I don't apply any restraint load. You don't need to buckle up. I don't apply any load to your body. You feel comfortable, right? Then I keep monitoring the surrounding. I see, okay, maybe 5% of situation, you drive on your car for 30 minutes to your work. There's 2 minutes, I sense, okay, the risk is high. Then I start to mobilize, to move the restraint to closer to your body. So I must have a device, something like a seatbelt, closer to your body, make it ready. If they're too far from your body, then when the collision coming, I don't have time to apply load. So I have to make the device closer to your body, but still make you comfortable. Then last second, 2 seconds before crash, I receive the signal. Okay, activate the device, or I make the belt tightened. So I only activate device when needed, make you uncomfortable. So you wouldn't complain with me, okay, because I only apply load 1% of your driving time. 99% you just drink coffee, right? And that's a decision, or that's an operation before collision, right? I don't guarantee I will make 100% correct operation, right? Just in case I made a mistake, I will reverse to normal. So basically, I don't use explosion. Everything will be reversible. So it's driven by motor, by actuator. You know, I tighten your body. Oh, okay, no, the risk is gone. So I make it reverse it. So this is I call it the uniform and adaptive restraint. Okay. We did some study over the past 10 years to see if we can do that. If we can do that, what will be the effect, the protection effect? We need to compare with today's airbag and seatbelt. Okay, so we use human body instead of dummy to analyze the situation. We found, okay, at least for chest, we will have a more symmetric and well-distributed deformation pattern on chest. Okay, for the same loading, if you can make your load more distributed, then the pressure will be lower, right? And the pressure will be lower. Then we can also well control the kinematic and posture. Then our study says the posture control is very critical for reducing injury. Posture is inclination. If you have very strange posture, or if your kinematical response is something like we call the submarining or some, so we want a posture something like that. This is a good posture. Under crash, and your body move forward as uniformly as possible. This is a good posture. So we can control your posture. And we have a simple study to compare. Okay, we compare the seatbelt alone, seatbelt plus airbag, that's today's countermeasure, and the double seatbelt. Double seatbelt, we don't use that, but just compare that. So two seatbelt. and the so-called uniform. You don't see uniform yet, but uniform is we apply the restraint load to 2 shoulders, to head, to chin. Then we compare 2 dummies, 2 body size, the average male, and the small female. That's 4 situation. Then we see if we have it's more and more uniform, right? More and more uniform.
Recording stopped. Recording in progress.
So that's uniform. When we make load more and more uniform, we see the injury probability going down. That's what we expect, right? And another thing is we have 2 body size. We use the same configuration of restraint. Cover 2 body size. We see they converge. Well, if we see airbag, seatbelt, they are different. So if we use today's airbag and seatbelt for different body size, your injury probability will be different. If your body size is different from the standard body size, then I'm sorry, right? Okay, so if we can apply the so-called distributed load or uniform load, then we see same configuration can cover wide range of body size, and even let's change load, we can cover wide range of crash severity. So that's a study. Then you would argue, how you do that? So that's all theory, right? So I also supervise some undergraduate students. So let's make some innovative structure and component, make it happen. So we sense in the future, autonomous driving cars, you don't drive car, computer will drive car. So you can sit in any direction, right? In any direction, you can recline. So the restraint must follow the seat. You should not put the airbag on the instrument panel because you might turn to the right side, right? So everything has to be mounted on seat for diverse seat environment and to convenient adjust everything you want. And we apply shoulder. We apply load to shoulder. So we have a shoulder bolster like this one, shoulder bolster. We have knee bolster like this one. Then we can change the angle of cushion, and we can change the height of seat back. If I see you're collected from behind, I change the position of head restraint. So everything is changeable, driven by motor. If I make the mistake, I'll reverse that. So I'll make those devices like when I sense the risk is high, I put it closer to your body, but not tightened. Then 2 seconds, 1 second before collision, I tighten that. So that's some innovation or some patterns we are applying for. Okay, this comes to my last part. It's all under study, right? And we haven't achieved that on a real product yet. But we'll continue to the study for the next 10 years. So we'll ask what tools and methods we should for design. And of course, we need many tools. But we'll probably address, human body models instead of dummy models with the diversity. We have different body size. And we will assess injury at the so-called tissue level. Tissue level means, our model has ribs, have aorta, have ligaments. So we'll see, if in my model, if the ligament deformation is too large, or the stress in the rib is too big, then we say, that could be the rib fracture. But today, we don't use human body model to design car. We use a dummy. We use a crash dummy. Crash dummy is a mechanical device. So the injury parameter is chest compression, chest acceleration, head acceleration. It's those mechanical parameters we can understand. So in the future, we'll use a tissue level. And we will assess many crash scenarios. There's too many to assess using physical tests, right? Using physical tests, use a real car. Then you can probably, for each car model, let's crash 10 cars. That's pretty expensive and time consuming. But what if you want to assess 100 scenarios? You test 100 cars, crash 100 cars, and you want to test different body size. So probably in the future, we will still conduct physical tests for 10 scenarios. Then for another 80 scenarios, we will use a virtual assessment to evaluate. So that's the tools. That's the tools I will need. Let me give you one example, right? Then Toyota and General Motors have developed two human body models, one called the SAMS, the other called the GHBMC model, and my group has been in that development or collaborated with developing group for 20 years, and so we did not develop, but we keep evaluating those. Then in the past few years, we did one thing. Okay, so we started with from the SAMS model. That's a human body model developed by Toyota. It has been in place for 20 years, still keep improving. But we found out we need to address the safety issue of Chinese body. And those model body sizes for US and European body. So one of my students, he spent probably almost 1 to 2 years to convert or to scale the European or US body size of SAMS model into Chinese body size. So we made the two Chinese body size, average male and small female of Chinese, and use the data from China data. Also, we spend money to buy those data, then convert it, so it's a time-consuming one. Then after we finish the model is, of course, we did not start from scratch. We start from Toyota's model. Then we test the model to see if it works, to handle the muscle effect and other things. And we also compare our models or our scaled model with the original model, to see, okay, they can work. They have different body size. This is a joint development between my group and Daimler under Oscar project. I'll come to the Oscar project later. Okay, I'm about to finish my talk, but I need to introduce, because most contents I introduced today is from the Oscar project. Okay, the Oscar project is a pretty big project. The title of the name of the project called the Future Occupant Safety for Crashes in Cars. So the title means we are developing safety protection means for future cars, for future autonomous driving cars. This is a public project sponsored by European government and the Chinese government. So you see the website, and this is a funding source. And this is 21 partners of the project. We are about to finish project at the end of this year and early next year. So you see all those partners you are familiar with: Volvo, Daimler, Volkswagen, Toyota, Bosch, Stuttgart, Chalmers, Aachen, and those software company, and Tsinghua University, and CARTEC, which is a regulation agency in China. So those 21 agencies, we made the effort of 3 years. So some contents I reported today are from that project. And what do we do? So this is a government collaboration between Chinese government and the European government. And basically we do 4 things. One is we assess a future accident scenario. That's what I reported today, the first part. We need to argue in the future, no matter how perfect of the technology, the autonomous driving vehicles will still incur accidents. So that's the main part, to assess future accident scenario. And the second part is we need to develop ideal protection means. That's what I call the uniform and adaptive restraint system. And to minimize injury, to provide individualized, reconfigurable restraint devices. Then we also need the tools like developing human body model and Chinese body size, and to reflect a muscle effect into the model. And what we haven't done is our European partner will do to make a virtual assessment method. So that's pretty much the 21 partner did in the past 3 years. We were in the effort for more than 10 years. Okay, I am about to finish, and to summarize, I have 2 more slides. If we consider the technology gap in vehicle safety protection, this is a summary I made. We see they are already good, but they are not to my satisfaction, probably not good to your satisfaction. It do not provide optimal protection to real accident. So it does provide protection to some standard situation. But if your collision parameters are far away from standard, your body size, your sitting posture, your collision speed are far from standard, then we do not provide best protection. That's the first thing, technology gap. And secondly, of course, do not cover China situation, because in China we only have 20 years of history the cars into market. Also, we are the #1 market, but technology-wise, and all the standard were based on European and the US. So it's not the best for Chinese body size and the China's accident data. And of course, it's not yet considered risk and accident of future cars, future autonomous driving cars, because future has not come yet. So those are what I summarized. We are still far from the safety satisfaction we want. And that's why we need to use autonomous driving technologies. We use those information to make protection preparation 1 second earlier, so we can do much better to provide individualized. That's pretty much summarized on this chart. Is normal driving. If you sense a risk, most of the time it's go back to normal. The risk is gone, right? Because you can intervene vehicle, right? Braking or the collision not happen. But 2 seconds or 1 second before collision, you cannot avoid accident. And you activate those devices I mentioned. Make the load, make the position best suitable to the upcoming collision, to the imminent collision, to the collision will happen 1.5 seconds later, to make it ready, then to provide it, then we can do better, because our judgment time, our preparation time is at least 50 times longer than before. Then our information is much more than before, right? So we can do better. That's our confidence for future. Last 2 slides for advertisement. I introduced the research of my group. Pretty much is 1 pillar, It's a human body protection to real accidents, not to laboratory environment. And we also have a big part on battery safety, which is another hot topic. I don't have time to introduce today. And also for material failure and the structure failure under crash loading. So those are the 3 research areas of my group. And this is the real last slides. And in Chinese. I do have my safety vehicle safety courses online, free. That's broadcasting you see today, channel today. Then you can find my course. Search my name. You can find that Chinese course. And I hope a year from now, I can have my English course available online, because we are recording today, right? And all right. So thank you. I'm finished my lecture, and so next half hour we'll probably have some question, answer, and discussions. So we are completing broadcasting.